Getting ready to start the session. So please take your seats quickly. Okay, so we'll have a very interesting presentation upcoming here. Will be about Numba. So this is a new dynamic framework for optimizing NumPy code and probably other things. So we have a presenter here will be Travis Oliphant, and we'll also have later on, I believe, John Ray. We'll have a very interesting presentation. So give them a very warm round of applause. So thank you very much.
All right, thank you, everybody. It's good to see you this afternoon. Welcome. Hopefully I'll show you some interesting things about some work we've been doing at Continuum Analytics along with our collaborator, John Reel. Forgive the jacket. Don't really try to intimidate you, but my wife has been trying for years to make sure I look nice, and my shirt's wrinkled. So it really helps hide the weight and the wrinkles, so don't worry about the jacket too much. A little about where I'm coming from. I kind of got into computer science or software development from a different angle. I really was a scientist. I was doing medical imaging. I was doing remote sensing, dealing with large sets of MRI data, ultrasound data, satellite weather data. I thought I would spend my life, designing better ultrasound machines or better MRI scanners or new pulse sequences. But I got kind of distracted by this whole Python NumPy world, Python SciPy world. And so sort of after years of developing SciPy, developing NumPy, I've kind of become I don't know if I really call myself a software developer, but I aspire to be one. And have recently sort of learned compiler technology and realized how to help this enormous community of NumPy users. So Python users are many, and there's software developers, there's web designers, there's web developers. Then there's this other subset of Python users who are NumPy users. They use NumPy all the time. Luke Lee gave a great demonstration of people that use NumPy. And they use it for doing array-oriented computing. And NumPy serves as the foundation of this very large ecosystem of all kinds of other packages that depend on NumPy as well. So it's not just NumPy. NumPy also has a C API that breeds SciPy, Matplotlib, scikit-learn, scikit-image. The list goes on and on. It's hard to estimate the number of users, but there's probably somewhere between 1 and 2 million users of these tools, which is very gratifying to see the adoption. Of course, it's a long history, and it's because it's the community effort that's gone into this. A little blatant ad here for NumFocus. There's a new foundation that helps support a lot of these tools. So if you're looking to how do you support NumPy, SciPy, NumFocus, a 501c3 foundation, just started last year to really help organize funding to help these projects continue to grow. So we're applying for membership, help us, donate now, all that stuff. All right, back to the story. So all these NumPy users are out there, and they're writing code because they can in Python that looks something like you might see here. They get arrays, and they want to do stuff with arrays. Like this example showed up on Stack Overflow. Someone showed, here's a formula I want to compute. I have some arrays. Give me this answer. How do I do it quickly? And I tried it in Python, and it was slow. And then you see all kinds of, in fact, I was just reading a blog post from the American, Johnny Lin from American Meteorological Society is saying Python is the next wave for Earth remote sensing meteorological studies. He said it's great, all these wonderful things about it. It is slow, kind of referring to people writing code like this and having it be slow, but maybe we can overcome that. I'm here to basically show you that can be overcome for a lot of code, that's very common that people write. This kind of array-oriented code. The other one on the bottom is a convolution kernel. It's nested for loops. You might see code just like this in C or Fortran to actually do a two-dimensional convolution. And here it is in Python, which is not that hard to understand either, except if you wrote it like that, your traditional NumPy vectorized Nazi would say, that's horrible, it's going to be slow, don't do that, pull out scikit or SciPy in the image or something else. So that's the state of the world to a NumPy developer, to a NumPy user, is Python's great, but it's kind of slow for these operations. So why is it slow? Let's take a hard look at this and see if we can't do something about it for NumPy users, for all this community of scientific developers. Well, one is the dynamic typing. The fact that at runtime, dynamic typing doesn't mean it's not typed. It means you write code and you're type agnostic. It means at runtime there is a type, you just don't specify in the code. And so there's no compiler that can say, oh, I know what to do here, and replace, instead of machine operations, you get attribute lookups and indirections and unboxing and a lot of extra code calls that happen before an operation gets done, even for something as simple as this I divided by j. Again, this is another Stack Overflow question. It's great. I can just go look at Stack Overflow at all these questions and speed them up. It's really kind of cool, actually. Attribute lookups are another one, but another one that is going to be at the bottom of some of the demos in here, and I want to kind of be upfront about it to begin with, is the NumPy get item is actually quite slow compared to, say, get item from a list. By get item, I mean the brackets, A bracket I, A bracket J. Getting an element, now it's fine if you're getting an array or you're getting a subregion out of NumPy arrays. That's really what the selector or the get item was meant for in NumPy. So that's what it's useful for, and it gives you back a view, it gives you back a new array. It wasn't ever really meant to be getting element by element out of the array and trying to do operations on it. So in fact, that's quite slow. Not only is the get item slow, but there's another detail. The scalar you get back is actually something called an array scalar, which is also not as fast as a float when you try to do arithmetic with it. So you'll see me do some comparisons here, and I'm comparing essentially against Python code with NumPy arrays. You can write Python code that's faster than the Python code I'll show, so the speed-ups are a little bit biased in that direction. So, but not hugely, just somewhat. Maybe order of 5, a 5x order. We're going to show speed-ups that are much, much larger than that. So it's just a 5x piece. So those are some of the reasons Python's slow. And so what do scientists do today when they want to write code that looks like that, easy to understand? I just have a for loop. I want to be fast. What do? Well, you hear of projects like Python, which has got a lot of attention, or traditionally people will just write their critical code in C, C++, or Fortran. They'll make a library of code. They'll hand it over to their guru that is a C++ developer or a Fortran developer. A lot of scientists actually just stick with Fortran and say, I just do all my code there. And then they might wrap it if they want to steer it and glue it together with other pieces easily. They'll wrap it in Python. They'll use tools like swig, C-types, f2py, fwrap. You'll see this wealth of tools that help people wrap their optimized code, and they do this mixed language dance, which is effective, if a little bit tedious, especially, and a little bit hard to teach too. More and more people are starting to write new codes in tools like Python. Python produces a C extension. It's decorated Python. And you should, if you haven't heard of Python, you should go take a look at it. It's pretty interesting. You add little type decorations, you change the Python syntax a bit, add type information to everything, and then it creates a C extension module, which is compiled and then loaded, much like NumPy is a C extension that's been written in C. So Python's the most popular these days, but speeding up NumPy-based code should be easier. There's so much information there. We ought to be able to speed this up much, much more quickly. And I've sort of wanted to do this for a long time. I've sort of known that this is kind of a weak side of the Python NumPy ecosystem and kind of been uncomfortable, and you want to try to do something about it. Those who don't know what a NumPy array is, it's pretty simple. It really is a typed container. If you're used to JavaScript, there's word of typed arrays coming into most JavaScript compilers these days. NumPy array is a typed array. It's a very fancy typed array, but at the bottom of the core, it just takes a wrapper around a chunk of memory and then tells Python how to interpret every element of that chunk of memory. And then it gives method calls. There's a shape information that tells you how to interpret that chunk of memory as a 2, 3, 4, 10-dimensional array. And the array scalar, when you actually grab an element out of a NumPy array, because NumPy arrays can be things like int8s or uint, unsigned integers, or 32-bit floats, instead of pulling back a Python scalar, it pulls back a special array scalar that also has that kind of precision, that carries around the actual data type. That's especially true when inside of your data structure, your NumPy array is a record. Maybe your array has, instead of a float, it has a string, a float, and a complex number, all together in one record. Now what do you pull out when you get an element? Well, you get an array scalar. Actually, it looks a lot like a named tuple, or the named tuples were recently added to Python. So, here's the idea. NumPy users are already using typed information. They're already using typed containers, regular storage, regular access patterns. There's plenty of information there for a compiler if you do one of two things. Either provide a little bit of information for a function about what the type information is. So if I look back at this code, the looped version, if I look at looped version that has 2 arguments, k and a, I don't know necessarily what k and a is, but if I just tell it, hey, k is going to be a NumPy array of type doubles, 2-dimensional NumPy array of doubles, and a is a 1-dimensional array of type of doubles, then there's a lot of type information, and a compiler can produce optimal code. The other approach is to do something called a call site, which is a word that I heard from the Iron Python folks. Call site just sits and listens and sort of watches, and when it gets called, now it knows what the types are. Right? You don't have to tell it what the types are going to be. You just wait and see when it gets called about what the types are, and then you generate code at that point for the types that you were called. A little bit of type inference to determine what the output types are, and then you produce the code. So that was kind of the idea. Let's use this type information that NumPy has and other type containers have to build tools that let people compile their Python. So there are several requirements for this work. One is it had to work with a CPython stack. We couldn't start another interpreter. We had to work with CPython just to get access to the wealth of tools that are already there. Luke Lee showed in the previous talk about how to build scientific applications. There's a lot of code out there that relies on the CPython stack. We wanted to stay consistent with it. Want minimal modifications to the code. In other words, use type inference. Don't force people to decorate all their code. Just say the particular pieces that need to be specified. Want control, the programmer to be able to control what gets compiled and what doesn't get compiled. Basically want an ability to have a build step. Want to be able to produce a static extension. If you look at the scientific Python stack, there's enormous numbers of extensions from matplotlib, pandas, has some extensions written in Python. You don't want to be jitting all those at runtime. You want to be able to produce static binaries you can ship and not have to pay the performance penalty on import time of compiling all that code. So you want to be able to control that and have that done in a more traditional way. And then also we want to be able to fall back to the Python C API whenever type inference can't determine what's there. If it's an object, if it doesn't know what kind of, it's a complex or a float or an int, we all can say is it's an object. It shouldn't die, it should at least use the Python C API and call something and do something intelligent. So we wanted to make sure that we satisfied that. Then we also wanted to produce code that wasn't just close to C, we want to make sure it was as fast as C. Maybe even our real target is actually as fast as Fortran, because like I said, there's a lot of scientific programmers who are still using Fortran because they say that's the way to get the performance code, the best performance. And that's our goal. That's who I want to target. I want those people not having something to stand on, have them all using Python. Want to be able to support NumPy array expressions. So you can still write vectorized code if it makes sense, because a lot of times it does make sense to express your ideas at a high level. And instead of writing a loop over every element of an array, just say y equals sine of x. That should also compile down to fast code. Want to be able to support actually the creation of these universal functions or these element by element functions that do calculations one at a time. In fact, I've wanted that for a long time. In NumPy, you'll see a function called vectorize. It's numpy.vectorize. And it was added because it's so often you want to be able to say, here's my code I want to run on a particular element of a large array. I can express it, now just make a universal function out of it so it can participate in broadcasting rules and casting rules and all the other things that are, all the other goodies that NumPy ufuncs have. Take this kernel and make it a ufunc. Well, that vectorize a little bit, it works, but what it does, it just uses object arrays, so it's really slow. It just converts everything to objects and goes to the Python interpreter every time. So it's not, I always wanted a fast vectorize. Wanted that for at least as long as NumPy's been around, and even before that. And then lastly, provide a tool that lets people think about writing their code, their NumPy-like code, and have a target or a pathway to run on a multi-core accelerators. Multi-core, the modern hardware that's coming down the pipeline, it's GPUs, Intel Xeon Phi is coming out, all these multi-core systems, and I don't want people saying Python can't be used and applied to those systems. It doesn't have to be true, and it shouldn't be true. And so NumPy has been able to take advantage of many cores for a while if you link against the correct library, and we wanted to make sure that people could write code that would do that as well. All right, so we want that, right? We want the world, we want everything. We want it to work nicely inside of what we currently have. So do we have to write it ourselves? Do we have to write the full compiler? Actually started that way a little bit. Fortunately, said, we're going to do it. There's nothing like a little ambition, right? And try to change the world. Fortunately, I met somebody who directed me to the LLVM compiler tool stack. I said, you know what, most of everything you want is right here. And I had to spend a bit of time understanding this because I wasn't a compiler guy, I didn't understand this. But I realized eventually that LLVM has done much of the heavy lifting. In fact, hopefully one thing you'll come away with this talk with is an understanding that LLVM can really bring compilers to everybody. A while ago, Guido had a project. I mean, if you've gone to PyCon as long as I have, you remember when Guido had a proposal for programming for everybody. Python is so simple to use and such an easy teaching language that you kind of get believing that everybody should be writing code. So programming for everybody was something was promoted a while ago. LLVMPy I think it kind of, going back to that spirit, it's compilers for everybody. You know, everybody can now write a compiler. It's not that, in fact, you really can with LLVM. In fact, I've got folks at Continuum who write compilers for, over the weekend. Happens regularly. So here's the face of a modern compiler, just for those like me who weren't steeped in computer science and don't know how to write compilers, don't really understand the context. It's not that difficult, minus the parsing and the code generation. Yeah, all the things I didn't have to do. So the face of a modern compiler is you have this front end step, parses the syntax, the actual text that somebody writes, converts it to some kind of intermediate form, intermediate representation, IR. You'll hear me say that a few times. So IR, and in fact, most compilers have several stages of IR, and that's sort of all the internal details. And then at some point, one of those stages, it compiles down to machine code. That's either x86, ARM, PowerPC, or GPU, PTX code. That's the back end, the code generation end. So I'm condensing up actually what might be a pretty extensible middle tier, kind of collapsing that into one. So Numba, which is our compiler which tries to tackle those requirements I just spoke of, it really just has to deal with, by using LLVM, LLVM does for us the IR, it does all the code generation, does multiple optimization passes, and it compiles to multiple backends. All we had to do was go from Python to that intermediate representation. And in fact, the Python parsing is already done for us as well. So really it becomes a matter of additional stages in the pipeline to go from one representation of a parsed Python tree to an LLVM IR representation, and then machine code, automatic machine code. It's been done before. I mean, if you talk to the PyPy guys, they've done this multiple times, in fact, in 3 different ways. This is not new. It's simply, let's take this technology, take this idea, and apply it to the enormous amount of code that's out there written for NumPy. And let's give it power to those folks and let them write their code the way they want to and still have it be fast. So an example, you take that code with multiple for loops that I talked about before, apply a simple decorator, AutoJIT. There's no arguments to this one, so it's not that particularly interesting, AutoJIT versus JIT. That for loop, that double nested for loop, you apply it through Numba, that decorator produces this intermediate representation. I'm showing it in textual form. In actual practice, Numba creates internal structures. It doesn't actually produce this text anywhere, but it creates the equivalent structures of this text. And you have this, and then the LLVM machinery, through llvmpy, can generate machine code giving you back a function pointer. You can think of it as if you've just created a shared object and loaded it with C-types, and now you're calling a C-types function pointer. In fact, it's very easy to take that function pointer and wrap it again with C-types and call it as if it were just a dynamic shared library. So this gives you a way to sort of generate machine code on the fly with Python code. It's actually a pretty nice concept, and LLVM and llvmpy provide that. So the idea of a Numba came from NumPy plus Mamba. I'm really not a great namer, but you know, I just throw something out there and hope it sticks. Numba's okay. Its core elements, though, are all this LLVM stack. I'd like to show this slide because it illustrates an important point about this compiler and why I think LLVM is an important technology, not just for Python, but for computing in general. It gives a place for cooperation. As we all know, separation of concerns is probably the only software engineering principle. It's probably the most important software engineering principle. It's how do we cooperate? How do we reuse code? How do abstractions actually come together and help each other share? The biggest success of NumPy, in fact, has simply been its use as a common abstraction that people can use together and cooperate about their notion of memory. And actually, we talk about it as if it was a bit of a work, but last time I was on this stage talking at PyCon, it was actually about the buffer protocol. The buffer protocol, which might be a line from some folks, really emerged from trying to merge NumPy into Python. We got NumPy into Python, it's called the buffer protocol. We just didn't get all the math. But with something like Numba applied to those buffer protocols, and all of a sudden you can think about producing NumPy pretty quickly, actually, from that. But cooperating together is the important key, and that LLVM library gives people who make the hardware an opportunity to, instead of having to write a full stack compiler, they just simply have to write, they simply have to write essentially a code generator, write a backend code generator to the LLVM IR. But they're motivated to do that, because if they do, they get access to an enormous wealth of tools of people who are targeting this IR for their hardware. So it kind of levels the playing field. I'm actually not sure if Intel loves that. I'm actually not sure if NVIDIA loves that. But they're having to participate because everybody's doing it. Apple spent a lot of resources, really, in fact, the PyPy guys spent a lot of resources too, helping the LLVM project, helping to improve and grow CLang. In fact, that demonstration I showed you before, CLang is in fact, uses LLVM as its backend. It just has a C++ parser for the semantics and the syntax of C++ on the front end to produce that IR. Okay, so the simple API, Numba is actually pretty simple. All that discussion was to help you understand, really kind of help wrap your mind around the idea that you can produce machine code from Python. And it's not that hard, and it can be done today, and it can make really fast code really quickly. If you use type containers. If you don't want to use containers that nobody has any idea what's stored inside of there, and we won't know at runtime, we won't know until you actually execute it. That was the problem the PyPy guys are solving, which is a much harder problem than what we're solving here. The simple API we have is just two decorators, JIT and AutoJIT. JIT allows you a little more control. It's the fastest to call at runtime because it just produces a native function pointer. It produces two things, actually. It produces a native machine code C function pointer, essentially, or C equivalent function pointer. Then it also builds a Python wrapper around that, so you can call it just as if you'd written a C extension around that C function pointer. So that's JIT. You have to tell it the types of the arguments you're calling. You don't actually have to tell it the return type. We'll do type inference on that, but traditionally, a lot of times the return type is also specified. So this example here, which is basically drawn from an example I'll show later about the Laplace, solving a Laplace 2D equation. It's an update step, and you can see it's just a for loop over a two-dimensional NumPy array where the elements are stored to basically update it with a single point with the average of the neighbors. And you don't call JIT and AutoJIT together. I'm just commenting one or the two out to show the difference. JIT, you specify the types, and it can produce a function pointer with a wrapper. AutoJIT, you don't specify the types. You just put it in the decorator as your function, and then it waits, and as soon as it gets called with specific types, it generates code for you, and caches that result, and then calls that optimized code again if you call it with the same types, or generates new code if you call it with different types. So there's a little bit more overhead for the dispatch. Obviously there's overhead for the compiling, but you only do that once. But there's a little more overhead for the dispatch, so sometimes I'll use JIT or AutoJIT. And so here's another example of taking the sync function, JITting that function, producing the IR, and that IR is equivalent IR as if I'd written that code in C or C++. I mean, so I do want to get across that once you type decorate your Python, it's equivalent as if you'd written C or C++, especially if you're using something like Clang to produce essentially the equivalent IR. So this really gives us a powerful tool to do things like real-time image processing in Python. Here's a simple example. 8 characters, essentially AutoJIT applied twice, one to the create fractal and then one to the internal Mandelbrot fractal converter, or determination of whether the iterations pause or not. Diverge or not, can produce 150x speed up with just a few lines of code. Really, it's kind of exciting because now I can write simple code, including complex numbers. Love Python for complex numbers. Want to make sure our compiler supports it as well. I can use complex numbers, and I can produce images very, very quickly. I can also take that example that was shown before on Stack Overflow, that looped version, and I just decorate it with AutoJIT. And now when I call that looped version, it looks like code that nobody would ever write unless they have Numba. Then you put the decorator on it, and now you have a C extension, or the equivalent of a C extension, if you've gone and put the work of writing that in Python or writing that in C, and the decorator makes it 1200x faster. Now that 1200x is an improvement over the NumPy, all those NumPy get items in there that are slower than if you'd done something different with nested lists. But nonetheless, that's the real benchmark for this case. And you can see it changes. It's 1200x speed up. It gets to about 200 or 300x speed up as your sizes get bigger, where a lot of time is spent copying a new array out. Image processing, if I have the nested for loops, and I grab an image off the web and just do a simple convolution filter, 1500x speed up is not uncommon. And one nice thing about using Numba is, this is a nice way to say it, I'm sort of avoiding the debugging question. How do you debug the machine code you generate? Well, yeah, let's talk about that for a little while. Instead, you just don't decorate, and you debug with Python. Just make sure to shrink your arrays, because you're going to have a hard time iterating over your, that's a big speed up. 1500x is a big speed up, so you don't want to be trying to iteratively iterate over something that goes to 30 seconds that only used to take a tenth of a second. So just shrink your arrays, debug your algorithm, and then speed it up with a decorator. One One new feature that we've just moved from a commercial product that we have as well into Numba, which is the open source version and BSD licensed, is array expressions. We want people to actually continue to write vectorized expressions. Write them like you would NumPy arrays. And with AutoJIT, what it will do is actually, at runtime, understand how you're calling it and really seek to try to optimize the compiled code that's generated. So it'll introduce all those loops for you and create code as if you had written this in NumPy. And that can actually be faster than what NumPy does. And there's just two examples of array expressions. What's what I mean by array expressions? I use the slicing syntax. I use operations with arrays. If you're familiar with NumPy, you know what that is. If you're not, that might look a little unfamiliar, but it works with Numba. And the one I'm most excited about, really, because it sort of started, it's the one thing I wanted so long ago, was this ability to create new ufuncs. And I'll show an example a little bit later. One of the very first modules I wrote in what became SciPy was a special function module. So as an engineer, as a physicist, I really, I like to solve differential equations. I like Bessel functions. I like Airy functions. I like all the spherical harmonics, all that wonderful stuff that has, you can put all kinds of math equations up and scare people and make them think you know what you're talking about. It's great, actually. But I wanted to compute those, and so I wanted this module in Python, but to do it, I essentially had to go out and scour the net, grab a bunch of Fortran code, grab a bunch of C code, link it, compile it, write a wrapper around it to expose it to as ufuncs in NumPy, and I was like, okay, great, we'll do this, and then everybody else will do this too, and we'll see if all kinds of special functions will emerge. And there were crickets in the hall, because nobody else was stupid enough to put in all that work to try to actually build ufuncs. So there aren't many ufuncs that get built regularly, right? Even though it's a really cool concept, and more ufuncs should be built because it's a cool concept, a cool idea. So now I think you can, with simple numba.vectorize, this will take your Python code, produce a machine code function out of it, stick that in the kernel of a ufunc, and now your ufunc has been created as fast as if you'd done it in C. So I was really excited about this, and that's currently in numba.vectorize. You can write your kernels in Python. And this starts to, some of you in the room, I hope, are thinking about, ooh, that could be parallelized too. Ooh, that could be used to target onto multiple cores or many of the little threads inside of a GPU kernel. And you're right, that really can be. And for a little while, we're trying to sell that. We know you guys are going to catch up with it and write that anyway, and so we're going to have to release that pretty quickly. But here's my case study. So here's my fancy slide with all the math equations on it. This is the Bessel equation. Just as for those who aren't familiar or wanted a little reminder about what the Bessel function is, the solution to this differential equation, ordinary differential equation, can also be written as an integral. These show up all over the place, particularly in cylindrical solutions to differential equations. So that's one of the first libraries I wrote. So here is the special function in Numba, right? So it barely fits on one slide, mostly because of all these little polynomials that are defined as arrays on the right-hand side of the slide. And then there's two functions, polyval and polyval1. They just simply evaluate a polynomial. One evaluates a polynomial when there's a 1 in the coefficient, so it doesn't have to do extra work when it already knows it's a 1 there. So that's why there's two of them. But in Python, they look pretty simple. When I JIT them, that creates machine code equivalent to what the C code was doing for these polynomial approximations. And then the Bessel function calculation is pretty much equivalent to what the C code was doing. You can see it's doing a ratio of polynomial approximation and for a particular region. That's typically how most of these special functions work, is they do some kind of approximation in different regions. And so you kind of have a bunch of if statements and then a bunch of rational approximations. Sometimes they get pretty weird. But you can do it all in Python and test it and evaluate it and figure it out. Vectorizing this, the result is my vectorized numbified function is the same speed as my SciPy special J0, telling me that I didn't have to do all that work. I just had to do all the work of writing a compiler first. But fortunately, I had a lot of help from great people like John Reel, Mark Florisson, and Siu Kwan Lam, as you'll see. I would argue that this code is more easily taken to a GPU, more easily adjusted, and you can apply all the great tools of metaprogramming, all the great cool things in Python for connecting this to other things, to other pieces. Integration is the story and is the important piece. Finally, I wanted to show an example that was adapted from a performance Python study that's made the rounds in the scientific computing space, as people try to say, how do I get more performance out of Python? This is this simple Laplace 2D equation. If you don't know what the Laplace equation is, it's a second order differential equation in space. You set it equal to 0, and there's a simple way to solve it just by iterating. You sort of assume a solution, and you just calculate every pixel. You calculate it as the average of its neighbors. You just do that for everything, and then do that over and over again, and iterate until it converges to a solution. That's what's happening here. This is the update step of that solution. The results, and this, I'm borrowing the numbers from some of the other solutions, or reran them again on my machine so they were all comparable. But Cython, Weave is another solution that embeds C++ inside of Python. NumExpr is another approach to doing this. There's the NumPy solution was one. This is illustrating that the Numba solution and the vector Numba, I didn't emphasize that, that's simply without the for loops. It's just using a NumPy array expression instead of the for loops, but it's also being sped up by Numba. So we get the best performance slightly. I mean, it'll be comparable. It should be almost exactly the same as a compiled solution. But it's nice to see that we are doing a good job of compiling this to code that's as fast as if we'd fed it through a C compiler. The only one that beats us still is the vectorized Fortran. And the vectorized Fortran example is when you take a Fortran 90 compiler and you give it an array expression, like I'm showing you there. They're doing some pretty nice things there. We'll have to figure out what they're doing and catch up with them. Because that's our goal, right? We want to make this the fastest way to write any code. I think Numba can change the game. And certainly I'm hoping to convince some of you to join us and help us continue to change the game. Because I think it really, I had that chart before about compiled technologies. It can really make Python, or a subset of Python, equivalent as if you'd written C or C++. So a lot of the stories out there of, oh, I got to prototype in Python, then I got to call out to C, or I got to rewrite this in C, doesn't go away. You can let them rewrite, and you can decorate, and you can go on to higher productivity. Right? So I think it's much more flexible as well, and I'm excited to see what people do with this. There's a lot of advanced features here I haven't talked about, and I'm going to get John Reel up here to talk about some of the developer features that are coming down the pipe. There are extension classes. I think auto-jitting a class was just added, but it hasn't been tested very well, so jump in. Struct support, NumPy arrays can be accessed. Their structure members can be accessed, so you can access records very easily. SSA, single statement, single static assignment, do I say that right? Can refer to local variables as different types. Type lists and type dictionaries are coming soon, other type containers, because that's really the key. You get speed because you have a type container. Pointer support, you can call C-types, that's a really cool feature. If I wrap a C-types library and I call it with Numba, if you get rid of the decorator, it goes through C-types. If you add the decorator, it doesn't go through C-types, it just uses C-types, which knows where the pointer is, and calls the pointer directly through the native code. So it just bypasses all the machinery and does native code calling. And then there's this PyCC tool, which actually creates either an extension module for Python, which you can then statically ship to somebody else and they can import, or it creates a static library with headers. So it's as if you wrote a C file and then created a shared library, but you did it in Python. So it's kind of fun. A lot of uses of Numba, blatant ad for Numba Pro. Go to our website if you want more information about that. I think it's really cool. It targets the GPU and so forth. But I wanted to talk about Numba development and try to encourage some of you to get involved. These are the folks that have really been behind making Numba happen. So I want to make sure and give shout outs to Mark and John and Sue. And John's going to come up here and talk about some of the features of where the project's headed. And there's a kind of a code count. You see that Mark's been particularly active. Mark is he's a very productive, prolific guy. He was a Cython developer actually too, and so a lot of the features of Cython have been moving over to Numba pretty quickly. Milestone roadmap 0.7 just released. We're going to get a 0.8 out in April sometime, 0.9 probably by June. Really targeting a 1.0 release by the end of the summer. There's a lot of things that need to happen before the 1.0 release, so it might slip a bit from the end of summer. The API though is very stable, so you don't really have to change your code much. You know, it's just did it work, or did you break, or did the compiler break on your code? That's really the only question you have to worry about. But ultimately, Numba should be sufficient, or should be in a state where I could have rewritten Numba, or NumPy, and SciPy. All that code that I spent decades writing could have been written with Numba. So that's the goal. I'm not saying that should be done. I'm just saying we want Numba to be sufficient at that place where it could happen if somebody more foolish than me got up there. John, I'm going to turn it over to you and let you talk a little about the architecture.
All right. Thanks, Travis. My name's John Reel. I'm too wearing a sports jacket. I think you should all be very, very concerned. Again, thanks, Travis. I really appreciate this opportunity to talk a little bit about Numba under the covers. I like to think that we're not just building a compiler for NumPy, but we're building a community of people who are building compilers using LLVM Py. And hopefully we'll be laying the framework or a foundation for people that want to piggyback off of Numba and build other kinds of specialized languages. So what we're looking at here is, I think in a previous slide, you saw an arrow going from Python to LLVM IR. That what you see kind of in that oval, in that rounded box, that's actually what the arrow expands out into. So again, we're using the Python parser to get a Python AST. This is our starting point. And then what we're doing is we have a successive set of stages that continually refine this abstract syntax tree until it's completely unrecognizable. And then finally, once basically, so these stages are things like type inference, converting for loops to while loops, and then ultimately getting down into the array-oriented specializations, and then finally we arrive at something that we can generate code from. And that in some sense, that's kind of a side effect at this point. Just in case you're curious, I encourage everyone to go to GitHub and go grab the source code. If you want to go look through the source tree, here's some of the entry points. So most of our JIT and AutoJIT decorators are in the decorators module. If you want to do anything with our pipeline, we have this kind of environment thing that has replaced global state. And then once you can construct one of these environments, you can pass it through our pipeline along with abstract syntax. And at the end, you get we have a code generator that takes that abstract syntax tree and generates LLVM. Travis showed a little bit about our milestone pacing. This is some of the stuff that I'd like to see before we hit 1.0. So we're talking about doing some refactoring here again to come up with modularity to make this more reusable. So I'd like to see us not just have use an abstract syntax tree that we mutate into an unrecognizable abstract syntax tree, but I'd like to have a stage where we can get you into an untyped but still static single assignment representation. Then from there, if you want to plug in your own type system, you can replace our typing system that's going to take that intermediate representation and generate types for it. But then we're going to generate a typed IR, and then based on the types that we annotate, we're going to then use that as a starting point to specialize to things like NumPy types. Right now, you also may notice that our inputs are functions. I'd like to greatly expand the PyCC story so that you can just feed us whole Python modules without any additional annotation. And of course, I think really one of the places where people can have an immediate benefit to the project if they want to collaborate with us is through helping us do better array specializations. So if there's a feature in NumPy that we currently don't do type inference for, this is an opportunity for you to go and add what we call a typing function that's going to tell us if I pass in this type and this other type to this NumPy function, then I'm going to get this type out. Very useful. That helps us specialize that code and avoid the object layer. As I said, we're building a community. We have over 20 authors in our authors list. We are on GitHub. We have a mailing list. And I'm happy to be here to put a face to my name. I'm going to be at the sprints starting Sunday. I think I'm also sprinting on some other projects I have. So if you look for the sprint Mython, Numba, and more, oh my, that'd be me. And then, of course, we've already had community involvement. Most notably, Hernan Greco. He's been really helping us a lot with getting Numba up to snuff with Python 3. But and then of course, I want everyone here to go home and pull and download Numba and come up with a killer app that says, oh my goodness, I thought that this was going to be impossible in Python, but thanks to Numba, it's sped up and it's now the possible has now become feasible. The impossible has become feasible. So, yep, that's it. I guess. Yep.
Any questions?
Thank you very much for your talk. I'll begin with a comment first. I'm a little worried about what you're doing here. I saw a talk earlier about job security in Python, and this seems to go very much against that.
There's a lot more C++ developers you can put out of a job.
You mentioned the community and the ecosystem that NumPy fits into. How would you use this type of technology to like speed up analysis within like a data frame?
Yeah, it's a great question. I think certain types could be added to Numba. I mean, it wouldn't be that difficult so that Numba can understand data frames and do the right thing under the covers. It would have to be educated a bit about the data frame, but it's certainly possible. I guess that would be the approach I would take. I mean, if somebody's writing a loop with a data frame, then you'd have to speed it up. Numba would have to understand that data frame object. But that actually gets to the point John brought up about making the compiler accessible. So it's easy to add that sort of thing.
Thank you.
Yeah.
This is something I might have missed toward the beginning of the talk, but when you pass in maybe an integer and then a rich type, like a Python object or something, do you just forego compiling the entire function for that type pair, or do you call back into the Python?
You call back into the Python C API. So you compile it, you just bypass the interpreter, you just end up with a bunch of C API calls.
Gotcha.
Yeah.
So Travis, I have to ask, for those people on Stack Overflow that post those inefficient algorithms, do you ever just respond with exactly what they posted and then the Numba decorator on top of it?
Yeah, I have.
So if you were going to write that kind of code like you were showing in C, you would get tremendously better performance if you declared with two keywords, const and restrict. And I was wondering if you are able to infer the const and restrictness of things, or if you're going to add another decorator or what?
That's a great question. We can infer a lot. Actually, we've sped up quite a bit. Some of my demos have sped up a bit because we're doing some more analysis and doing that kind of constant pointer. But that's probably a better question for John. Mark Florisson, he's not with us, actually, probably answer that the best.
Actually, because we're using static single assignment, generally it's, I can't remember the other talk. There was another talk, I think, at maybe the Python versus Swig talk. Anyway, basically when you assign something to, when you assign a constant to a value, because of the intermediate representation we're using, it's just treated like a constant. So any further assignments to, actually everything that's assigned a constant is treated like a constant until you change the value, at which point we come up with a fresh value, actually, and then further code points down the road we'll use that definition as opposed to the constant. So yeah, constants work really well, and do we do constant folding? I know, okay, great, right. So Siu wrote
Siu, why don't you stand up, Siu? This is Siu, he was on the talk list, but he didn't have something to say. This is a developer on Numba.
So right, when we see constants going into something that we know how to evaluate at compile time, we're also doing that.
What sort of overhead does the initial compilation introduce in the runtime?
Yeah, so the import, and that's a good question. The compilation happens on import time with JIT and on call time the first time with new types on AutoJIT. It varies. I mean, we're not really optimizing the compiler at this point, so it might be a second, it might be half a second, it really depends. That's one of the reasons actually the PyPy project didn't use LLVM after a while, because it's not particularly known as a very fast compiler. And so, but our approach allows us to not have to have the fastest compiler in the world.
Okay.
So.
Thank you.
So Python's a really dynamic language, and so how do you handle cases where people will reassign built-ins or globals, or even how do you handle changes in closures around functions that you've decorated?
Yeah, that's a great question. There's several great questions. Well, on the built-ins, we just ignore their changes. So, I mean, obviously there's a restricted subset here. I mean, if you call the math.sign function, for example, if somebody else monkey patches at that, well, we've already compiled it. It's gone. So it's sort of, that's one way. On the closure side, I mean, Numba actually supports closures. It stores them as static. I mean, I don't understand your question well enough. I don't think I can answer it very well. I have to leave maybe Siu or Mark or John. Do you want to tackle that one?
No, closures were Mark Florisson, so I need Mark.
Yeah, a lot of times we punt. I mean, the general answer is we punt, right? And so we kind of have definitely a subset of the language, and we fall back to Python if we can't speed it up, right? And so ultimately, you put a decorator, the worst that happens is it doesn't do anything and just calls CAPI calls. Maybe gets rid of the interpreter overhead, maybe, but.
So it's a best effort with a fallback to
It's a best effort with a fallback, exactly.
Thanks.
Yeah.
I was going to ask about constant folding, and what other strength reduction or other kinds of things are you including, and is that in that set of intermediate representations?
Yeah, the LLVM compiler, one thing about the intermediate representation, there's a lot of optimization passes that it does, and so if we can put intrinsics and little sort of labels, then the optimizations of LLVM will actually do a lot of speed up for us.
Right.
So we've done that a little bit with something called TBAA.
Yeah.
So you're getting the constant folding for free out of LLVM, not doing it on the ASD?
Yes, exactly.
Okay, great, thanks.
Yes.
You mentioned typed sets and dictionaries, and those sound really incredibly useful to me.
Yeah.
How close are they?
So typed lists are there, but they're early beta, and start pinging the list, and what you care about will probably get done first, right?
Okay.
Yeah.
What do the Julia people think about this?
You know, I gave a talk at Siam with a Julia person, and I was doing it, and then somebody from R. We're all using LLVM, right? And so essentially, we're just decorating LLVM differently with a little bit of different run times. I think they're interested. I mean, certainly there's a lot of work going into intermixing Python and Julia. I don't know if you saw, like Fernando Perez has made the IPython notebook so it can call out to Julia instead of a cell. And so there's a lot of intermixing going on. I think, for one, I think some of what we're doing with Numba makes a lot of the stuff they're doing with Julia not as interesting to a lot of people. Julia's still an interesting project, and it has a nice type system we're learning from. But I think interop is the key. I mean, to me, interop is what I shoot for. I love integration. I love people to use what they have and not be too pedantic about, you can't use Julia, you can't use this. Use it all. We'll just make it work together.
Great. Thanks.
So.
This question is in the context of redistribution, perhaps even closed source redistribution. So one of your early requirements in one of your early slides implied to me that you want to be able to JIT ahead of time and save that as perhaps a compiled Python extension. Could you say more about how that works, particularly if you're only JITting 2 or 3 functions in a module with a whole bunch of Python functions? What's the deliverable then?
Sure, yeah. I mean, John, maybe you want to talk about that?
Right now, we really don't handle that case, I don't believe. I would think that we're going to have to come up with some sort of way of being able to embed bitcode into Python PYC files, which is something I've worked on in Python before, and it's totally doable. And,
a lot of approaches, very doable, a lot of approaches. We haven't settled on exactly the right approach. Right now, to do the distribution, you have to have everything JITted, right? You can't have a mix. Everything's either JITted or you're shipping a Python.py file. But the mix is not difficult, it's just a matter of deciding what to do, how to do it. All right.
I have a quick question about the AutoJIT. You said it's type inference is done on the first time you call it. Is that correct?
It's done every time you call it with a different set of types.
Oh, I see.
Right. AutoJIT, it sits there and waits when you get called with different types. It has to do new type inference.
But you generate a code for only one type and cache only one call?
Yes, you cache code for that one call, and then if it gets called with those same types again, it just calls the cached machine code.
I see.
If you call it with different types, it'll redo essentially the compilation stage.
Okay, thanks.
Yeah. Go ahead, yeah, John.
That's also a really interesting use case, because Mark Florisson, who's also a Python developer, there's currently is working on supporting a scientific enhancement proposal through NumFocus.
It's just where it's located, yeah.
Yeah. So what we have here is the idea of taking a type signature and creating a hash key, and then different extension providers can basically provide each other with a kind of like a virtual table that's indexed by these hash keys. And so if you're interested, you can read more about it at NumFocus at the Scientific Enhancement Proposals.
So can you just use multiple decorators then to pre-declare multiple entries in that hash table?
You could, you potentially, right. Right now, the JIT has to be the last one. Well, not necessarily. Vectorize can go on top of that. Okay. I'm actually available at the booth. I'll be there until 5 at the Continuum Analytics booth. If you have further questions, I think we have to end the session. Is that okay? Those who don't know what a NumPy array is, it's pretty simple. It really is a typed container. If you're used to JavaScript, there's word of typed arrays coming into most JavaScript compilers these days. NumPy array is a typed array. It's a very fancy typed array, but at the bottom of the core, it just takes a wrapper around a chunk of memory and then tells Python how to interpret every element of that chunk of memory. And then it gives method calls. There's a shape information that tells you how to interpret that chunk of memory as a 2, 3, 4, 10-dimensional array. And the array scaler, when you actually grab an element out of a NumPy array, because NumPy arrays can be things like int 8s or uint, unsigned integers, or 32-bit floats, instead of pulling back a Python scaler, it pulls back a special array scaler that also has that kind of precision, that carries around the actual data type. That's especially true when inside of your data structure, your NumPy array is a record. Maybe your array has, instead of a float, it has a string, a float, and a complex number, all together in one record. Now what do you pull out when you get an element? Well, you get an array scaler. Actually, it looks a lot like a named tuple, or the named tuples were recently added to Python. So, here's the idea. NumPy users are already using typed information. They're already using typed containers, regular storage, regular access patterns. There's plenty of information there for a compiler if you do one of two things. Either provide a little bit of information for a function about what the type information is. So if I look back at this code, the looped version, if I look at looped version that has 2 arguments, k and a, I don't know necessarily what k and a is, but if I just tell it, hey, k is going to be a NumPy array of type doubles, 2-dimensional NumPy array of doubles, of people that use NumPy, and they use it for doing array-oriented computing. And NumPy serves as the foundation of this very large ecosystem of all kinds of other packages that depend on NumPy as well. So it's not just NumPy. NumPy also has a C API that breeds SciPy, Matplotlib, scikit-learn, scikit-image. The list goes on and on. It's hard to estimate the number of users, but there's probably somewhere between 1 and 2 million users of these tools, which is very gratifying to see the adoption. Of course, it's a long history, and it's because it's the community effort that's gone into this. A little blatant ad here for NumFocus. There's a new foundation that helps support a lot of these tools. So if you're looking to how do you support NumPy, SciPy, NumFocus, a 501c3 foundation, just started last year to really help organize funding to help these projects continue to grow. So we're applying for membership, help us, donate now, all that stuff. All right, back to the story. So all these NumPy users are out there, and they're writing code because they can in Python that looks something like you might see here. They get arrays, and they want to do stuff with arrays. Like this example showed up on Stack Overflow. Someone showed, here's a formula I want to compute. I have some arrays. Give me this answer. How do I do it quickly? And I tried it in Python, and it was slow. And then you see all kinds of, in fact, I was just reading a blog post from the American, Johnny Lin from American Meteorological Society is saying Python is the next wave for Earth remote sensing meteorological studies. He said it's great, all these wonderful things about it. It is slow, kind of referring to people writing code like this and having it be slow, but maybe we can overcome that. I'm here to basically show you that can be overcome for a lot of code, that's very common that people write. This kind of array-oriented code. The other one on the bottom is a convolution kernel. It's nested for loops. You might see code just like this in C or Fortran to actually do a 2-dimensional convolution. And here it is in Python, which is not that hard to understand either, except if you wrote it like that, your traditional NumPy vectorized Nazi would say, that's horrible, it's going to be slow, don't do that. Pull out scikit or scipy in the image or something else. So that's the state of the world to a NumPy developer, to a NumPy user, is Python's great, but it's kind of slow for these operations. So why is it slow? Let's take a hard look at this and see if we can't do something about it for NumPy users, for all this community of scientific developers. Well, one is the dynamic typing. The fact that at runtime, dynamic typing doesn't mean it's not typed. It means you write code and you're type agnostic. It means at runtime there is a type, you just don't specify in the code. And so there's no compiler that can say, oh, I know what to do here, and replace, instead of machine operations, you get attribute lookups and indirections and unboxing and a lot of extra code calls that happen before an operation gets done, even for something as simple as this I divided by j. Again, this is another Stack Overflow question. It's great. I can just go look at Stack Overflow at all these questions and speed them up. It's really kind of cool, actually. attribute lookups are another one, but another one that is going to be at the bottom of some of the demos in here, and I want to kind of be upfront about it to begin with, is the NumPy get item is actually quite slow compared to, say, get item from a list. By get item, I mean the brackets, A bracket I, A bracket J. Getting an element, now it's fine if you're getting an array or you're getting a subregion out of NumPy arrays. That's really what the selector or the get item was meant for in NumPy. So that's what it's useful for, and it gives you back a view, it gives you back a new array. It wasn't ever really meant to be getting element by element out of the array and trying to do operations on it. So in fact, that's quite slow. Not only is the get item slow, but there's another detail. The scalar you get back is actually something called an array scalar, which is also not as fast as a float when you try to do arithmetic with it. So you'll see me do some comparisons here, and I'm comparing essentially against Python code with NumPy arrays. You can write Python.
Getting ready to start a session. So please take a seat quickly. Okay, so we'll have a very interesting presentation upcoming here. Will be about Numba. So this is a new dynamic framework for optimizing NumPy code and probably other things. So we'll have a presenter here will be Travis Oliphant, and we'll also have later on, I believe, John Ray. We'll have a very interesting presentation, so give them a very warm round of applause. So thank you very much.
All right, thank you everybody. It's good to see you this afternoon. Welcome. Hopefully I'll show you some interesting things about some work we've been doing at Continuum Analytics along with our collaborator, John Reel. Forgive the jacket. Don't really try to intimidate you, but my wife has been trying for years to make sure I look nice, and my shirt's wrinkled. So it really helps hide the weight and the wrinkles, so don't worry about the jacket too much. A little about where I'm coming from. I kind of got into computer science or software development from a different angle. I really was a scientist. I was doing medical imaging. I was doing remote sensing, dealing with large sets of MRI data, ultrasound data, satellite weather data. I thought I would spend my life, designing better ultrasound machines or better MRI scanners or new pulse sequences. But I got kind of distracted by this whole Python NumPy world, Python SciPy world. And so sort of after years of developing SciPy, developing NumPy, I've kind of become I don't know if I really call myself a software developer, but I aspire to be one. And have recently sort of learned compiler technology and realized how to help this enormous community of NumPy users. So Python users are many, and there's software developers, there's web designers, there's web developers. Then there's this other subset of Python users who are NumPy users. They use NumPy all the time. Luke Lee gave a great demonstration code that's faster than the Python code I'll show. So the speedups are a little bit biased in that direction. So, but not hugely, just somewhat. Maybe order of 5. A 5x order. We're going to show speedups that are much, much larger than that. So it's just a 5x piece. So those are some of the reasons Python's slow. And so what do scientists do today when they want to write code that looks like that, easy to understand? I just have a for loop. I want to be fast. What do? Well, you hear of projects like Cython, which has got a lot of attention, or traditionally people just write their critical code in C, C++, or Fortran. They'll make a library of code. They'll hand it over to their guru that is a C++ developer or a Fortran developer. A lot of scientists actually just stick with Fortran and say, I just do all my code there. And then they might wrap it if they want to steer it and glue it together with other pieces easily. They'll wrap it in Python. They'll use tools like Swig, C-types, F2Py, FWrap. You'll see this wealth of tools that help people wrap their optimized code, and they do this mixed language dance, which is effective, if a little bit tedious, especially, and a little bit hard to teach too. More and more people are starting to write new codes in tools like Cython. Cython produces a C extension. It's decorated Python. And you should, if you haven't heard of Cython, you should go take a look at it. It's pretty interesting. You add little type decorations, you change the Python syntax a bit, add type information to everything, and then it creates a C extension module, which is compiled and then loaded, much like NumPy is a C extension that's been written in C. So Cython's the most popular these days, but speeding up NumPy-based code should be easier. There's so much information there. We ought to be able to speed this up much, much more quickly. And I've sort of wanted to do this for a long time. I've sort of known that this is kind of a weak side of the Python NumPy ecosystem and kind of been uncomfortable, and you want to try to do something about it.